Part B. You got a rational function, kind of, right? Polynomial divided by polynomial, but one of them has a radical in it. So we want to figure out the end behavior. Whenever you see a limit, you want to make sure that you carefully figure out, though, what it is, if it's handed to you, what you're approaching. Because you can get real excited and see something like this and be like, ooh, ooh, ooh. I remember there's kind of a trick. You got to get the number first and the sign second. But if the limit is like asking you to approach 0, then direct substitution works. So make sure you read carefully. But we do want the end behavior here as we go to the right. So kind of the same thing we did in the previous problem. In the top, it is an actual 2x cubed leading term. And the bottom, it is growing effectively as if it were a square root of 11 to the 6th, which is 11's not a perfect square, is it? No. So it would be the square root of 11. And what would be the square root of x to the 6th? X to the 3rd, right. You just take half the power to square root it. So they are effectively the same degree, x cubed over x cubed. So the magnitude of the quotients is what you're after. Just because it's negative here doesn't mean it's going to be negative on either side necessarily. So I do know for a fact that the answer is going to be some type of 2 over the square root of 11 on both sides. It may be negative on both sides, maybe positive on both sides, maybe one of each. Because there's a radical and it's the square root of an even power, the bottom is always positive, isn't it? See that? The bottom is always positive. So again, if it were truly an x cubed over x cubed, we wouldn't have to check because positive over positive is positive and negative over negative is positive. So we would just be left with the leading coefficients. So let's go ahead and check the sign, essentially, of the numerator, right? You plug in a positive infinity into the leading term. Negative 2 positive cubed is negative. And we already said the bottom is positive, so negative over positive is, in fact, negative. So as you go to the right, you do get the negative. But as you go out to the left, in the top, negative cubed is negative times negative 2 is positive. So you end up with positive over positive, which is, in fact, positive. Yeah, and I've caught many students over the years giving something like this as a multiple choice answer, and they just kind of go like that, and they take the negative. So make sure, if you see that radical, that you get the number first and then the sign second. All right, any questions on that one? A, B, C is next, and it's yours. It's all yours. Big K of X. I'll get it. I bet it's Slater. It's Slater. Look at that. Hello. Always practice proper notation in your notes, too. It's real easy to let yourself off the hook when it doesn't matter, but then you're just reinforcing bad habits, bad notation. K and K of X here could stand for careful of X, right? If you misspell it properly. I guess there could be a proper way to misspell something, right? Anybody got an answer? Zero. You have zero answer, or that is your answer? It is your answer. You have one answer, and it's zero. On which side? Right or left? Both. Yeah. Yeah, very good. So again, you kind of get excited, like, ooh, 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 right? Number first, sign second. But the first thing you have to do is analyze the growth rates, right? The top is an actual negative 5x squared, or just a 5x squared, if you want to do that. The bottom is the square root of 11 to the 6th, which again is just the square root of 11, x to the 3rd. Okay, so that's the effective growth rate. And the bottom is still growing faster than the top. And anytime that happens, your ratios decrease towards 0. Now, what you could do if you wanted, since 0 is the line of demarcation between positive and negative numbers, if you did want to plug in a positive or negative into your leading terms, you would be able to determine whether it's approaching 0 from above or below the x-axis, as we did earlier, but it is 0. So there is only one horizontal asymptote. So k of x has a at y equals 0. Don't forget y equals. You should never just have a number sticking out there at 0. It should always be labeled x equals, y equals, whatever. And then I didn't summarize very well over here because we had two different end behavior limits. The function g of x did have two horizontal asymptotes, okay? So just be on the lookout for radicals. They look very similar to rational functions, like on example 3, but they stick out. And again, the radical doesn't necessarily have to be in the bottom. That's just the examples that I have. You also want to be careful, too, because in all three of my examples, the radical part was always positive, but you could very easily have a negative sticking outside of a radical. And now the denominator is always what? For values in the domain. It's always negative, yeah. Or you could have like another number out there, like a -3, and now you would include that. Now the effective growth rate in the bottom is negative square root of 11 x to the third. So there are variations of that, okay? But that's the basic idea. Okay, any comments or questions on that? We're kind of just learning things in isolation. All of this is going to culminate in Chapter 3 when we put all this together to kind of sketch awesome graphs with shading and stuff like that. They're going to be beautiful masterpieces. Okay, here we go. Limits at infinity, bonus problems. We'll get through this pretty quickly. Bonus problems. So at the end of the year, we are going to be working with exclamation points quite a bit. And that kind of goes without saying all year. We're excited, right? And we exclaim everything we do when it comes to math. But that exclamation point is also a math symbol. So if you ever play golf with a bad golfer, you've probably heard that English expression, right? Unless it's the ball's heading towards somebody you don't like and you maybe don't exclaim it, you know. You just say, hey, you're going to get hit, right? But for exclamation point in math, we read that as for, anyone know? Yeah, factorial. Okay, so maybe I've seen it before. Y'all have read. Good. We call that factorial. And what it is it's that integer, that positive integer, times all of the other integers that are positive down to 1, not 0. Otherwise, it'd be 0. So 4, 3, 2, 1. So basically, let's come over here. N factorial is defined to be the, oops, let me spell correctly, the number of ways to arrange n objects. Okay, the number of ways to arrange n objects. That's where it comes from. So it comes from the field of probability, or what's called combinatorics, the way to combine things. So let's say that you have 1, 2, 3, 4. Okay, you have 4 positions to fill in. Let's call it, I don't know, the math club. Okay. You have the president, you have the vice president, you have the secretary, and then you have B, the bouncer, to keep everything under control, right? You need one. And then you have 4 people running for the positions, and those 4 people are the only people who volunteered because they're the only people in the math club. And so they're all going to get a position. How many different ways can you assign the executive office of the math club? Yeah, very good. It's like this. There are 4 ways you could choose the first position, whether it's president or bouncer, and that leaves only 3 people. And so now there's 3 different ways you can choose the vice president, which means then there's only 2 ways you can choose the, sheriff? No, secretary. That's the bouncer's job, sorry. And then the bartender is going to be, the bouncer, golly, it's just the guy who's left over. There's only one way to choose the bouncer. So, yeah, and those are independent events, and so we learn to multiply independent events together. So 4, 3, 2, 1 is 24. There's 24 different ways you can have that club, all right? So that is known as 4 factorial. So it's a pretty nifty little sign. Okay, so what we're going to do now is look at the sequence of growth for different families of functions for large values of x, magnitude-wise, okay? We're going to take some liberty here. I'm getting ahead of myself. I left factorial a little bit too soon. Sorry. How about what is 2 factorial? We'll just do that. What is 2 factorial equal to? 2, right? It's 2 times 1. What is 1 factorial equal to? 1, right? Good. What is 0 factorial equal to? 1? 0? 1? 0? 1? I don't know. Let's see. Let's go back to 1 factorial. If you have one object, let's say you have a shelf, right? Here's a shelf. Okay, so it hangs on the wall. There we go. And maybe a nailing board right here. Okay, good. There we go. We got a shelf. And you have one object like, I don't know, a basketball. No, we don't put basketballs on shelves. Let's call it a book. Okay, let's do a book. There's a book. We have one book, right? How many different ways can we arrange one book on that one shelf? One, right? There's only one way, right? You just take this and you put it up here. I mean, you can put it wherever you want, but there it is, right? So 1 factorial is 1. All right. Now, let's say that you don't read. You don't have a book, okay? How many objects do we have now? 0. 0 books, right? We as illiterate. How many ways is there then to arrange the 0 books on one shelf? How many ways can you arrange 0 books on one shelf? Believe it or not, we say there's one way. The fact that there are no books to put on there means that that is a way to arrange the shelf. You arrange the shelf in no particular fashion, and that counts as a particular way. But it's the only way, right? Okay, you can't pull negative books off the shelf. And therefore, 0 factorial, Felipe, is what? You were right. It is 1. 0 factorial is 1. And you can verify it on your calculator. You can get to the factorial symbol on, like if you hit math, whatever, you can investigate. But you can type in 1 factorial and 0 factorial, and they'll both give you 1. Okay? So this is kind of cool, right? 1 factorial equals 0 factorial. And, of course, the factorials divide out, which means 1 equals 0. Right? Very good. No, they don't. So that's kind of cool, right? Now, if someone walked in right now and they didn't know what factorial meant, they would be like, okay, yeah, I agree, 1 doesn't equal 0. But thinking that that's an exclamation point, they'd be like, oh, if you say it with enough enthusiasm, though, sure, 0 and 1 are the same. But you have to really believe in it, right? Okay, anyway. Let's prove that. We're messing with factorial today. You can define n factorial recursively. Okay, recursively means that it depends upon previous iterations to develop the next. We can define that as n times n minus 1 factorial. So we'll be doing that a lot in the end of the year. So in other words, an example would be like 4 factorial is equal to 4 times 3 factorial, right? Y'all buy that? And of course, then 3 factorial would be 3 times 2 factorial, so on and so forth. That's called recursive relation because it relies on the previous thing. So let's go ahead and use this definition, recursive definition of factorial to actually prove, because some of y'all are like, you can't arrange 0 books one way. I'm like, just look right there. There it is. That's the way. It's one way. We'll prove it mathematically so that you are convinced. Let's go ahead and we'll let n equal 1. Let n equal 1. And we'll plug it into both sides of this definition. So we get 1 factorial equals 1 times 1 minus 1 factorial. And so that gives us 1 factorial equals, let's see, 1 minus 1 is 0 factorial, and 0 factorial times 1 is 1. And there's the proof. It's an easy little proof. Yeah. So 1 factorial is equal to 0 factorial. And, of course, 1 factorial is equal to 1. So they're both equal to 1. Kind of neat. Okay, kind of nifty. So anyway, that's the factorial function. Now we're going to take some liberties here, and we're going to define it as x to the factorial power instead of just positive integers, or I guess I should say whole numbers, really. So that's going to be a new function that we're going to be analyzing, the factorial function. How does that function grow compared to other functions like polynomial or exponential? And then we have the another function, which I'm going to say is the queen of all growth. We'll use q of x then for that reason. And it's of the form x to the x. It's kind of a hybrid polynomial that has a variable base and a numeric power, and an exponential that has a variable power and a numeric base. This one has a variable base and a variable power. And this is called the Aleph function. This is Aleph 1. That's kind of a weird word. If you throw another x up there, x to the x to the x, you get like Aleph 2, so on and so forth. But we'll just work with this one. So anyone know the significance of the word aleph? Any Old Testament scholars here in the original language? Anyone know Hebrew? Yeah, I don't either. But apparently, Hebrew kindergartners have to learn the alphabet song, and the first word in that song is aleph. So that's A. That's A in Hebrew, aleph. So anyway, there you go. That's the aleph function. So we have two new functions. You're not going to see them in any of your graphical computations, but I throw them in here because it's kind of neat. So let's look at this box right here. This is a list of functions by how fast they grow for large x in increasing order. If you ever go on to take discrete mathematics, a course like that, if you want to become like a computer programmer, you're going to learn about a function called the big O function, okay? And that's how you write it, with a big O and then a x. It's called the big O function. And what it does is, computer software engineers, they want to be really, really careful about how fast their program runs or builds up big numbers, because computers would rather work with smaller numbers and do more calculations than do fewer calculations with big numbers. That's how computers crash, when they work with big numbers. So if they could draw out the process and make the number smaller, but maybe do 10 times more work, computers are fine with that. And so they're really concerned with how fast things grow. And that's where the big O function comes in. So here it is in increasing order. The slowest growing function for large values of x is k, where k is a constant. Okay? That makes sense. How fast do constants grow? They don't, right? They stay the same. Now, growing pathetically faster than constants is the family of log functions. Logs grow marginally faster than constants in the long run, right? In the beginning, they grow pretty rapidly. But if you remember the natural log of x, it curves and starts leveling off pretty fast. It does grow to infinity, just very, very, very slowly. Okay, now within the hierarchy of log functions, we actually have a hierarchy. So like if you want to work down, they also grow faster the smaller the base. So like log base 10 grows slower than log base 9. We'll do that like that, which grows faster than the natural log of x, which is log base e, so on and so forth. It's kind of the reciprocal of exponential. Okay, so there's the hierarchy within there. Now, growing faster than log functions are power functions. We call these power functions. These include all of your polynomials, like x squared, x cubed, x to the fourth, which we've already worked with. But they also include all your radical functions, like the square root of x, because it's x to the 1/2, right? X to the 2/3, stuff like that. So again, these have their own hierarchy. For the larger the n, the faster the growth. And we know that, right? Like an x to the fourth grows faster than an x squared, so on and so forth. So what grows faster than power functions? These forms b to the x. These are your exponential functions, okay? And they also have their own hierarchy. So like the larger the base, the faster the growth. So e to the x grows faster than 2 to the x, 10 to the x grows faster than e to the x, so on and so forth. The logs are the ones that are backwards, okay? And that's pretty much the catalog that we're going to see, because those are the functions that we've studied, through pre-cal, and that we're going to use quite a bit in here. But I do want to throw these in, okay, because that's why this is the bonus problem section. Growing faster than exponentials are your factorials. Yeah, factorials grow faster than exponentials in the long run. And again, they have their own hierarchy here. The larger the x, the faster they grow. But what grows faster than factorials? The queen of all growth, the aleph function. Okay, the x to the x. They kind of trump everything, right? They grow the fastest. And then they have their own hierarchy too, because you can have x to the x to the x, and then you can have x to the x to the x to the x, and then it starts getting really, really crazy how fast they grow, okay? So there you go. This is kind of helpful to remember, at least remembering it up to here, okay, for sure. Constants, then logs, then power functions, polynomials, radicals, and then your exponential, for the most part, are the kings of y'all's growth. But, queens trump kings all the time. All right, example 6. Let's try it out. Evaluate the following by analyzing the comparative growth rate of the numerator and the denominator. So, again, when you have an n behavior limit, whether it's plus or minus infinity, and you're analyzing a ratio of two functions, all you have to do is see which one grows faster. If the top grows faster, it's some type of infinity. If the bottom grows faster, it's always going to what? 0. And if they grow at effectively the same rate, it's always the quotient of their coefficients, okay? So we're going to infinity here. We got x cubed over 1.01 to the x. Which grows faster, top or bottom? Bottom, right? In the long run, the bottom is exponential, the top is cubic. So in the long run, this will go to 0. Now in the short run, if you want to think about this in the short run, x cubed looks like this. It's pretty steep right away. And then 1.01 to the x does like this. Okay, there's the y-intercept 0, 1. And notice it's barely exponential growth. It's only growth if the base is greater than 1. So in the short term, x cubed is flying past 1.01. But it's like the tortoise and the hare. Because x cubed gets cocky, takes a nap, and 1.01 passes him somewhere down the line, and x cubed cannot recover. So that's why we're talking about way down the line, huge values of x, okay? Good. Y'all got it. Letter B. Look at that. That is starting off strong. That's huge, right? But where does he go from there? Nowhere, right? All over a simple linear function that subtracts values of cosine of x squared? Any idea? It is 0. Good. Your intuition serves you well. This is a constant, which is the slowest growing function because it doesn't grow. You have a linear function like this. Values of cosine of x squared could be positive or negative, right? They could actually be anything between -1 and 1. So it's really, we can treat that almost like a constant, almost, because it stays bounded between two constants. So it's kind of like a line that's being, maybe sometimes adding one, subtracting one. If you were to graph this function, here's kind of how it would look. If you graph the line of 5x, all you have to do is kind of like snake it like this. Snake a cosine graph around it, and that's kind of what the function looks like. So it does increase. It goes to infinity. And even though 999 may be way up here, you know, we have forever, and it'll pass it eventually. So yes, it does go to 0, okay? All right, letter C, going to infinity, natural log of x over the 9th root of x. This is like a battle of last place right here, kind of. Natural log of x grows slowly, 9th root of x, not in a hurry to go to infinity. But someone's got to win. Yeah, it is 0. Because 9th root of x is x to the 1/9, which belongs to the power function family, which grows faster than any logarithmic growth function. So yeah, it does go to 0. Good. Okay, 100 to the x. That is impressive. If your money grew according to that exponential function, you would be the richest person on the face of the planet. That's pretty extremely fast growth. Wow. But
students, just a reminder, if you want your transcript, that office will close in 5 minutes at the end of this lunch. Thank you.
You're welcome. But we got the queen in the denominator, right? It goes to 0. It goes to 0. Okay? And again, you answer these very quickly because you've kind of memorized that sequence of growth. A, B, C, D, E comes next. Go for it. You see a theme developing here, right? This is a pretty exciting one. This is like the Super Bowl. It's like the two champs going at it, but the Super Bowl lasts forever. Wow. And ultimately, the queen wins at the end of the game. That never ends. Yeah, so it does go to 0. Yeah, good. A, B, C, D, E, F. Oh, how about F? What you think, Armstrong? That's a good safe answer. I like that. That would be a good free response answer. What would be a better multiple choice answer? Infinity. Yeah, infinity is a better answer. Yeah, it doesn't exist because it increases that bound. Because now the top grows faster than the bottom, and we don't really even have to check the sign because x is going to positive infinity. Positive is a positive or positive. Everything's positive, right? Rachel's Challenge graduate. Okay. All right, A, B, C, D, E, F. Do we have any more? No, that was it. Okay, so anyway, this is going to show up periodically throughout the year. We'll do it again later in the year when we talk about improper integrals, and we'll come back to this, okay? So if you can kind of remember this sequence, at least up to here for now, and maybe even with factorials in there, then you're in good shape, okay? We're probably not going to see the Aleph function, but now you know about it. Okay, let's see if we can finish off here. There's two examples. They're very, very similar. We have 2 minutes. We have the limit as x goes to infinity, okay? As x goes to infinity, look at the terms of the variables. What's happened to 3 to the x as x goes to infinity? What's essentially 3 to the infinite power? It goes to infinity, right? It goes huge, right? So for huge magnitudes in the top and bottom, do you think 8 and 4 are contributing? No, that's like a little pipsqueak trying to help you do a chore. They want to help. It's like, okay, you can help. And they're just kind of getting in the way. They're insignificant. This is like infinity, and it's like if you give like a billionaire like a penny, they're like, thanks, I needed that, right? They don't feel it at all. So this is effectively 0. That's effectively 0. And so now we can just look at, like with polynomials, we can look at the leading term over the leading term. The top is growing pretty much the exact same rate as the bottom. They're both the same base, right? 3 to the x, 3 to the x. So just as if it were like x cubed over x cubed, it would be leading coefficient over leading coefficient, which would be what? Negative 1 over 1, or negative 1. Now, if that had been 3 to the x in the top and 4 to the x in the bottom, now it'd be 0, right? Because 4 to the x in that family of exponentials grows faster. All right, last one here, 30 seconds. Now as we're going to negative infinity, ooh, that's different. What happens to 3 to the x as x goes to negative infinity? Well, that's 3 to the negative infinity, which is 1 over 3 to the infinity, which is approaching what? 0. So exponentials have dramatically different end behaviors. On one side, they're infinite. On one side, they're 0. So as we go out to the left, these are the things that are becoming insignificant. And now the things that are dominating the numerator and the denominator are the 8 and the 4. What's 8 divided by 4? 2. And that's your answer, because that's approaching 8 minus 0 over 4 plus 0. So you have a couple like that on your worksheet. We're done with this section. Perfect, perfect timing. Enjoy the rest of your Barbie doll day. And remember, tomorrow's cheese day, so wear your cheese clothes.